So if we assume independent two pseudo-random permutations and the sum, then we get a 4-bit secure pseudo-random function. It's very nice, and it's a provably secure construction. But now we have question. Do we really need PRP here? So E and E prime is a pseudo-random permutation, then of course it's no problem. But if this E and E prime is insecure block cipher, what happens? Actually, these questions already arised by the Banik et al. TOSC 2021. So they say E and E prime are rather weak as a standalone block cipher. For example, reduced down block cipher. And key point is output of E and E prime are invisible for attackers. So of course, the attacker if attacker want to break this sum construction, attacker can only learn the output of the sum, and attacker never check the output of each permutations. In that case, probably E and E prime is much weaker block cipher. Maybe this sum construction should be secure, as a pseudo-random function. So they propose the complete construction orthodox, so by using this observation. So maybe the conclusion is PRP might be over security to construct pseudo-random function by this construction. So now we want to analyze this construction more general view, but of course the most general view is a very provable security discussion, so that we assume PRP and then PRN. But unfortunately in this case, it's unlikely to be possible to weaken the assumption from PRP. So, but if we use a dedicated analysis like the orthodox designer, then it is a new primitive, new analysis from scratch. So it's a very heavy to analyze this construction. So heavy to analyze the new primitive. It's a very heavy cost to design. So now we want to bridge these two cases. And now we want to introduce general practical cryptanalysis. So we analyze this construction like the dedicated analysis, but we don't support each specification. So like the generic attack on phase network. But we also consider the link with another construction like the security reduction. So this is our initial dream. So of course, this is a dream. So the left side is a P plus Q, and right side is a P of Q. So it's an iterative construction or sum construction. So our initial dream, if attacker can break the sum construction. If in that case, he can break the PQ construction, then of course it's a very nice. But it's too nice because this is a reduction security. So if we can prove it, so it's of course P plus Q is equivalently secure to the iterative construction. But of course, this is dream. So unfortunately, it's impossible. So now we need to wake up. So reality from dream. So now what we do is we restrict attacker. So now we restrict attacker is a differential cryptanalysis, linear cryptanalysis, truncate differential, and so on. Several kinds of attack, and we apply as this attack, these two against these two constructions at the same time, and compare the security. Interestingly, for some attack, for example, differential cryptanalysis, if the sum construction is broken by the differential, so some attacks, then we can also break the compositions by using the same idea with high chance. How to do it? Okay, so now this is a differential cryptanalysis. So I think the differential cryptanalysis is the most simple, so maybe I explain the differential cryptanalysis here. Okay, so now alpha is input difference, and beta is output difference. And differential probability is defined by probability satisfying f of x plus f of x plus alpha is equal to beta. So this is the definition of the differential probability. And so now now, so that of course, we can sort of define the same differential probability to the composition. But of course, these two probabilities are different. But now, if for the attacker, for practical cryptanalysis context, maybe we never use differential probability in practice. So instead, we usually use differential characteristic probability. In this case, the left side, alpha is the input difference, is the same, and gamma is the output difference of the P, and beta is the output difference of Q. Then the resulting output difference is beta plus gamma. And differential characteristic probability is defined by the product of the differential probability for P and the differential probability of Q. So we can define the same differential characteristic probability to these iterative constructions. And I think it's a very natural construction. So alpha to gamma to beta, and the gamma is the intermediate difference. And differential characteristic probability is the probability product of the P and Q. It's the same. But it's a bit different. So now I change the construction a little bit. P inverse instead of P. In that case, so we know differential characteristic probability is exactly the same. The left construction, right construction has exactly the same differential characteristic probability. So usually, when we mount the differential attack, we first build the differential characteristic and we evaluate differential characteristic probability. And we say differential characteristic probability is very close to the real differential probability. So now we get, yes, these two differential probability is very close to zero, both in the composition construction. So now this is summary. So the differential construction have, of course, different differential probability. But in practice, to mount the attack, we use the differential characteristic instead of differential. So in that case, both constructions have the same differential probability. But of course, so the differential probability is much accurate security evaluation, of course. So when P and Q are independent, so in that case, the differential probability is defined by the sum of the differential characteristic probability. So the left case, so the alpha, beta plus gamma is a fixed, and the differential, so the differential probability is the sum of the differential characteristic probability activating gamma. But the right case is also very similar. So differential probability is the sum of the differential characteristic probability with while activating the intermediate difference alpha. So it implies that these two probabilities are different ways of adding the same value. The total number of the added value is the same to the n. And each, so the summed value is the same. But this is a different way of the sum. So actually, so after we know this, so the relationship, our next motivation is to build some counterexamples. So for example, the left construction is weak and right construction is strong. And right construction is weak and left construction is strong. So we want to build such a counterexample, but I can't. It's very, very difficult to build these two constructions that has a different differential probability. Okay, so after here, so we say about the differential probability, but now we want to extend this idea to differential key recovery. So for simplicity, so we start the discussion from the iterative structure, and maybe everyone knows. So in differential key recovery attack, we first decompose the cipher into 3 sub-ciphers, and the middle is the differential probability, and top and last is the key recovery part. But key recovery part is regarded as a truncated differential with probability 1. So alpha to beta is the differential probability, and so from alpha to plain text, we have the truncated differential, and beta to the ciphertext, we have truncated differential. So if we guess the correct K0 and K2, then the data complexity is, of course, P inverse. Of course, at least P inverse, because if we, of course, in practice, we don't know the real key. So there is a case, the number of data complexity is higher than P inverse, but at least P inverse. It's a very important, at least P inverse. So there is a possibility that data complexity is exactly P inverse in this case. So now we want to apply the differential key recovery to the sum construction. So in this case, so we have several strategies. So this case, so that we apply the key recovery to the output side, but it's very difficult. So alpha P, alpha Q is intermediate difference, and we have some differential probability for the top part. And now we want to apply the key recovery to the ciphertext part side, but attacker only knows the output of the sum of permutations. So from output difference, so that we can take arbitrary difference for each branch. So it's very difficult to append the key recovery to the output side. So natural idea is key recovery to the plain text side, because plain text is known by attacker. So in that case, so that we first have the differential, we first estimate the differential probability from alpha P to gamma and alpha Q to beta, and the product is a probability P. And so we apply the truncated differential from alpha P to the plain text and alpha Q to the plain text, and we have the same attack. But unfortunately, this attack doesn't work, because from alpha P to plain text, it's no problem, because the truncated differential is probability 1. But plain text is connected. So even if we ask a P inverse data, but this data, we cannot guarantee this data satisfies the alpha P input difference and the alpha Q input difference at the same time. So we need to multiply the probability Q. Q is defined by the differential probability from alpha P to alpha Q. So even if we know the correct P, we need to at least P inverse times Q inverse pairs. Otherwise, we cannot do that. Okay, so next, how about linear cryptanalysis? So differential cryptanalysis, we use differential characteristic equivalence from the plain text via plain text set and compares to the iterative construction. So in the case of linear cryptanalysis, it's a different way. We consider the linear trade via the ciphertext output side, and we also have the same discussions. But the structure is a bit different. So S star is a P Q inverse, but the differential is a P inverse Q. So it's a bit different. But in practice, S star is almost equal to S, because this case, so the left side is the differential case and right side is the linear case, P inverse Q and P Q inverse. But now, so that we first consider the inverse functions for the linear case. So in that case, the QP inverse. And if P inverse is iterative structure with the round function R and RP times, and Q is also RQ times, and it uses the same round function with different Q. In that case, so that S is RP plus RQ rounds, and S star inverse is also RP plus RQ round. So it's the same. But one interesting is linear key recovery attack against the sum construction. So unlike the differential cryptanalysis, we don't have any dependency issue. So we can append the key recovery. So we have linear probability, linear expected linear correlation probability from the intermediate to the ciphertext, and we can append the key recovery to the top. So it implies that linear cryptanalysis is more promising strategy than differential cryptanalysis when we consider the freedom of the key recovery. Okay, so this is summary. So unfortunately, so that is the time is limited. So I only discussed the differential and the linear, but we discussed several kinds of attack. For example, differential linear key recovery is equivalent to the differential linear, and second order differential is equivalent to Boomerang, and between the middle is we have similar strategy. But of course, it's not perfect. So for example, truncated differential linear, and integral, we have several results. But the integral attack, in particular, the integral attack can be most critical because the algebraic degree is the maximum degree of either POV. But semi-constant key recovery attack, differential type attack has the same dependency issue. So this rule attacks. So it's very, very difficult to append key recovery to the secret key distinguisher. Okay, so now finally, I want to introduce instantiation. So this is the AES 128. So 10 round cipher. How to do it? So first we cut, and first is a 5 round, and the next is 5 inverse round, and dip. So but in this case, so the R input of the R inverse is so the directly visible by the attacker. So we just change the key X positions like this. So this is the zip AES. So now finally, so we discuss security analysis of zip AES, but we inherit almost the same security analysis. For example, differential linear, so there's something differential linear, the second order differential is the same. But of course, we need to analyze some exception. For example, so that autocorrelations or integral or truncated differential. In this type of attacks, bit difference, so that we need to analyze from scratch. But for original differential attack or linear, something like this, we don't need. Okay, so finally, I want to discuss the performance. So to compare the performance, I implemented the AES and the ASPRF and the zip AES. But AES, of course, and with counter mode. But of course, the AES is a block cipher, so not a should random function. So in the counter mode, AES is a birthday bound security. But the ASPRF and zip AES is a should random function. So it's if we use the counter mode, it's an NBC. So security level is different. So when we compare the both three constructions, we know zip AES is a nice relationship for the small data because AES and ASPRF need the 10 round depth, but the zip AES is only 5 round depth. But for long data, zip AES is a bit worse than other two constructions. This is because AES new instruction. AES new instruction supports AES inverse functions, but this function is a bit different from the natural inverse round functions. Natural inverse round function is a mixed random inverse, flow inverse, subarray inverse around T. But AES deck of AES9 is a subarray inverse, flow inverse, mixed random inverse around T. So it's a bit different. And if we want to apply mixed random inverse only, mixed random inverse is a double slower than round function. So this is the main reason why zip AES is much slower than AES and ASPRF. So to solve this issue, so we changed the counter from integer counter to the gray code counter. Gray code counter is linear. Update is linear, so the mixed random inverse is of course linear. In that case, the impact of the mixed random inverse is absorbed to the plaintext and the counter, each counter. In that case, we can avoid mixed random inverse for every block, and throughput is improved. So in that case, yes, zip AES is for long data, so there no drawback. Okay, so this is the conclusion. So we propose a general practical cryptanalysis. So this is the analysis of the cipher without detailed specification like generic attack. and compare the security from well-studied construction like a reduction security. And the sum is almost equivalently secure to the compositions piece. And if we consider the key recovery attack, the sum construction is much difficult to attack. And also, unfortunately, I don't explain in the talk, so that we also reported the error in the existing analysis against all source because of the difficulty of the differential critical work. And finally, we propose the zip AES. This is construction the cut AES and zip. Thanks. Thank you.
So any question from the audience? Yes.
So when you have a function and then the inverse, this reminds me a bit of reflection ciphers. So if you have a reflection cipher, you have a function, something in the middle, usually very simple, and then the inverse. Can you somehow relate this construction to the sum of two parallel functions? In this case, you would have the same function. You do not have to have the inverse because one is already inverted to the other side.
But it's a different construction. So the X then, so it's sort of like so Prince or yeah, so something right. In that case, the long functions and reflections and inverse. So maybe in this case, let's see, and that. But it's from here and input is here and output is here. But this is random functions, and from here and output is this. So it's a different construction. So
Yes, no.
yeah.
But initially you have P and Q. So if P is the inverse of Q, what happens? So the only difference would be the P.
Yes, so like this.
But yes, but the function. But you would not have R and R inverse, you would have the same R.
Yeah, of course, R and R inverse is no. Yeah, so it's a very important part. So if we use R instead of R inverse here, then we don't have any link to the original this construction. So if we want to discuss the security link from here, between here and here, then so that here R inverse is necessary. In that case, so the differential probability is equivalent, differential characteristic probability is equivalent to the original construction.
Okay, I think we had one question on this side.
What is the security claim of zip AES?
128 is secure to draw the function.
Okay, thank you.
Any other question? Okay, so I had a related question. So did you try using this exercise on other ciphers as well?
Yeah, so one interesting question is AES 256 key value. In that case, the 7 plus 7 1, a 7 encryption and 7 decryption. And I'm not sure that it satisfies 256 key. And also the interesting instantiation is the 64-bit block cipher. In that case of for example, git 64 or CD 64. So maybe 64-bit blocks, the bus about security is only 32 bits. But in this construction, the security level is a 64 bit. Okay. Probably it's a secure part in practice.
Yes.
So I think the 64-bit block and then discussing this construction is very interesting.
Okay.
Open question.
Okay. If there are no more questions, let's thank the speaker again. Okay, so the next talk is on key collisions on AES and its applications, and it will be presented by Kodai Taiyama.
Thank you for your introduction. My name is Kodai from University of Hyogo. Today, I will talk about the automatic tools for key collisions and how to apply these tools to AES. Here is the outline of this presentation. We will start with an overview of the research and some background knowledge, followed by an explanation of the tool proposed in this study. Finally, we will briefly discuss the results of applying the tool to AES 256. Let's begin with the overview. This is about the new variant key collision defined in this research. In block ciphers, key collision is defined as two distinct keys that produce identical subkeys through the key scheduling function. When such colliding keys are used, any plaintext can be encrypted into the same ciphertext. On the other hand, we defined a new variant of key collision called the target plaintext key collision. This refers to two distinct keys that generate the same ciphertext for a single target plaintext. In this study, such collisions can be classified into two problems: fixed target plaintext collision and free target plaintext collision, depending on whether a single target plaintext is predetermined or not. The previously explained target plaintext key collision relates to key committing security. Albertini et al. Proposed incorporating padding fixes into AES, GCM, and CHA 20 poly 1305 to address their lack of security. This leads to the following open problem. Is it possible to find two keys K1 and K2 such that AES K10 equals AES K20 in less than 2 to the power of 64 trials? This predetermined zero input is what the study considered as the target. And moreover, the target plaintext collision attack can be converted into a collision attack on the DM hashing mode. As shown in the figure, the condition where different key inputs produce the same output for a given target is the same in both cases. DM hashing mode is one of the most important hashing modes, but this type of attack has not been investigated for AES over the past 20 years. We believe the following two problems are the main reasons for this. Problem one, key difference should be canceled out by themselves. Problem two, a limitation in controlling plaintext. Conventional MIP-based exploration methods and super-box techniques are not effective in addressing this problem. So to address this problem, in this research, we proposed an automatic tool for finding target plaintext key collisions. And this tool utilizes bitwise differential characteristics explored by a such solver, and additionally, it automatically groups the internal states into independently computable components and evaluates the computational complexity. We apply the proposed tool to each variant of AES, and we have revealed for the first time the results of collisions and simultaneous collisions in AES-DM. Moreover, we experimentally verify the validity of the proposed attack, especially on the pre-target plaintext collision attack on 9 round AES 256. An attack method for two-block collision is also discussed in the paper, but due to the time limitations, we will omit in this presentation. Now, I will explain the details of the research. First, I will explain the specifications of AES. AES is a block cipher that supports key lengths of 128, 192, and 256 bits. The round function of AES consists of the following 4 operations: some bytes, shift rows, mix counts, and a drum key. Next, the rebound attack. The rebound attack proposed by Mendel at FSC 2009 is a generic tool for cryptanalysis of hash functions, especially on AES-like hashing. It is primarily divided into 2 phases, inbound phase and the outbound phase. The inbound phase aims to find as many value pairs as possible in target cipher in where the differential probability is low. And the number of value pairs obtained in this phase is referred to as the degrees of freedom. Next, in the outbound phase, the degrees of freedom are used to find values that satisfy the differential characteristics, that satisfies the differential characteristics of the entire cipher. In this research, we performed a bit-level rebound attack to finding colliding pairs. Next, we will explain the tool we propose. First, the tool includes approaches to address these 2 problems. This tool utilizes bitwise differential characteristics explored by such solver, and additionally, since techniques like the supersbox box method can be effectively applied, so we adopt an approach that groups the internal states automatically. The tool proposed in the study consists of 6 main steps. I will now explain these steps in order. In step 1, we explore the differential characteristics where the difference between the message input and output is 0 using a sub-based tool. For details on the modeling, please refer to the paper. Next, we convert the explored differential characteristic into a graphical expression. As shown in the figure, for instance, S13 and K03 are each defined as 32 bit vertices, and each vertex is connected to others through XOR, shift rows, and mix counts operations. These 32-bit vertices are units of internal states whose values we can independently determine. For example, even if the value of K00 is determined, it does not necessarily determine the value of K10. Next, we determine the attack range and check whether the starting point of the attack is valid or not. If the target is AES 256 and the plaintext input is predetermined, we can select 8 vertices as the starting points for the attack. Therefore, in this step, we select 8 vertices that include nonlinear layers and determine the order in which their values will be calculated. And next, we determine the degrees of freedom, which is the value that satisfies the difference in the vertices. If the total probability contained in the inbound vertex is 2 to the power of -p, then the degrees of freedom on the inbound vertex can be expressed as 2 to the power of 32 minus p. If the value of the degrees of freedom is more than 2 to the power of 0, the inbound vertex is considered invalid and the attack based on those starting points is aborted. If the starting points are confirmed to be valid, the next step is to group each vertex and construct a dot tree. First, let us assume that the value input into the plaintext are already determined. This vertex is defined as group GIV, and its dot is 2 to the power of 0. The number inside the circle represents the maximum degrees of freedom that can be utilized, and the G below the circle indicates the group. And first, let's suppose that the value of the vertex indicates as in 1 in the figure is grouped as an inbound vertex. If the total probability contained in 1 is 2 to the power of minus p, then the degrees of freedom is 2 to the power of 32 minus p. Since GIV and G in 1 are connected by an XOR operations, once the values of these two vertices are determined, the values of the vertices in the key scheduling function are also determined. The values of the vertices in the section colored blue are determined by the two values. In the dot tree, 2 to the power of negative q represents the total probability contained in out 1, which is colored blue. In this way, we sequentially group the inbound and outbound vertices, constructing a dot tree that illustrates the dependency of the values. Finally, we calculate the attack complexity using the dot tree obtained in step 5. In this presentation, we will explain under the assumption that dot tree, like the one shown on the left, has already been constructed. Each numerical value mentioned here is an integer. Furthermore, dot in K represents the maximum degrees of freedom that can be used within a given group, while prob out K indicates the total probability within that group. This constraint represents the amount of values actually used in the attack. Dot in K represents the maximum usable degrees of freedom and limits the variable in K in uppercase, which is it indicates the number of values used in the attack. Since there are 3 inbound vertices, the constraints indicated from 1 to 3 are added. Next, this constraint represents how many values are carried over to the next outbound phase. Here, uppercase out K in uppercase represents the number of value pairs that satisfy the difference. Additionally, prob out 1 represents the total probability of the group at 1. These two constraints 3 and 4 make it possible to represent degrees of freedom calculation during the outbound phase. Finally, we introduce the constraint for the time complexity. As shown in this figure, obtaining the value of out 1 requires 2 to the power of in 1 plus in 2 computations. To address this, we introduce a new variable, T1 max, and define the constraint as T1 max less than or equals in 1 plus in 2. Then, by solving the problem of minimizing T and demonstrating that the result can be obtained with fewer than 2 to the power of 64 computations, the attack can be considered successful. Finally, I will briefly explain part of the grouping of attacks on AES 256. This figure shows rounds 5 through 8 of AES 256. Using this figure, we will briefly explain the order of grouping through exploration. First, we inbound the vertices from bit 96 to 128 of round 7. At this stage, the value of all other vertices have not been determined, and it is not possible to explore other vertices. Similarly, we inbound the vertices of round 7 one by one. Each inbound vertex is assigned to a group from in 1 to in 4. Once the 128-bit value of round 7 is determined, the shift rows and mix comps operations can be performed, and it has the 4 values to mix. The blue card section consists of the 4 inbound vertices, so it is assigned to the group of out 1. Next, we inbound the vertices from base 96 to 128 of round 8. As a result, the out 1 group from round 7 and the in 5 group from round 8 are connected by an XOR operations, and it allowing the exploration to proceed to the key squaring function colored purple. The purple section is outbound based on the degrees of freedom of the out 1 group and the degrees of freedom of in 5, which can be determined independently. By sequentially performing the inbound process, the vertices in the green card section are determined. In this way, by performing the inbound phase starting from the 128-bit values, we can independently handle the probabilities of the nonlinear operations in the Q-scheduling function. As a result, the attack complexity can be significantly reduced. This represents the amount of value pairs actually used and their dependencies in degrees of freedom. Since the probability of 2 to the power of negative 30 is dominant in this case, it can be concluded that the attack can be performed with a computational complexity of 2 to the power of 30. In the study, we performed experimental verification under the symmetry start collision of AES 256 The experimental setup is as follows, and within approximately 12 hours, we were able to discover value pairs where collisions occur. And the table below shows the actual plaintext and key value pairs where collision occurred. Here is a summary of this presentation. We define a new variant of key collision called the target plaintext key collision, and we propose an automatic tool for key collisions. It utilizes, this tool utilizes bitwise differential characteristics explored by SAT solver and automatically groups the internal state into independently computable components. And it then evaluates the computational complexity. We apply the tool to AES 128, 192, 256, and uncovered fixed target plaintext key collisions. We have uncovered the results of fixed target plaintext key collision and free target plaintext key collisions. This is the results of applying the tool. That concludes my presentation. Thank you for your attention.
Thank the speaker. Okay, any question from the audience? Okay, so yeah, I had one question. When using your tool, you are trying to find this, target plain text key collision. So are you assuming that the subkeys will not collide, or that possibility is also considered?
Sorry,
So, so one variant is that two different keys, due to the key scheduling, is giving you the same subkey, right? And then that might lead to your collision. That is one possibility, right? The other possibility is that you don't look into the subkeys, you look at the ciphertext at the very end.
yes.
So what I'm trying to say, when you are considering the second possibility, then are you excluding the first, that no subkeys will collide? I mean, you are ignoring that?
Sorry.
So you're starting with two different keys, right, to begin with. So my question is, two different keys can lead to target plaintext key collision by two ways. One by subkey collision and one by without subkey collision. So are you considering one of the two possibilities instead of both? That's my question.
Sorry, I'm not
Okay,
sure.
maybe we can talk about it later. So also you can go to your table, the last table that you had here. Okay, so in AES 128 DM, your number of rounds that you penetrate is relatively small compared to other work.
Yeah.
So any reason for that? Or, I mean, why you will need, I'm guessing you will need more complexity, right, to go into the other rounds, which is like much beyond 2 to the power 52, right? So the question is, why does it become difficult to penetrate more rounds, like free start case?
You mean so collision and similar start collision is so
You have 2, 3, 5, right? So
yes.
yeah, so which is less than 6.
So AES 120.
Also 6, 9, 9 is less than 14. So
6, 9, 4. AES 128 has so 3-rounded maximum differential characteristics probabilities, so less than 2 to the power of negative 128, so we cannot attack 3-round
okay.
collision. Right.
Okay, any other question? Yes.
Yes. For 9 rounds into ACE 256 and 3 rounds in 128, you're getting 2 block collision. Why it is not happening in for a smaller number of rounds case?
Sorry, what? Could you repeat that? Sorry.
Can you repeat the
So,
question?
okay. So if I'm understanding correctly, this 2 block collision means, I mean, 2 into 128, right? This for 9 rounds, you are getting collision. And for a smaller number of rounds, like 6 rounds, you are getting single block collision, if I'm understanding correctly.
So he's asking that for smaller rounds, are you having single block collision?
Sorry, say one more.
Maybe you
Okay.
can talk later.
We'll discuss
Next
offline.
time, yeah, during the coffee break.
Okay.
Okay, let's thank the speaker again. The next talk will be online, so I request the organizers to set up the system. So, hello, Jan, can you hear us?
Yes, can you hear me?
Yeah, we can hear you. Maybe you can adjust the sound a little bit. Sound is fine? Okay. We have something on the screen. Okay, so the next talk will be online. The Boomerang chain distinguishers, new record for 6-round AES, and the talk will be given by Yan. Okay, you can begin.
Okay, thank you. Hello, everyone. My name is Yan Xueping. I'm honored to have the opportunity to make my presentation. Today's topic is the Boomerang chain distinguishers, new record for 6-round AES. Let's first recall background. AES is the most widely used symmetric cipher. There's no known attack on 4 AES faster than exhaustive search. The security evaluation on round-reduced AES is also an important problem, where the distinguishing attacks have attracted much attention of scholars. This table shows the current secret key distinguishers for 5 and 6 rounds of AES. At present, the 5-round AES distinguishers on AES include multiple of 8, exchange, and UU, and they all have the data complexity less than or equal to 2 to 32. For 6-round AES, the distinguishers include truncated differential, exchange, and truncated boomerang, where the best result is provided by the exchange technique. In the chosen plaintext setting, the exchange distinguisher for 6-round AES has data and time complexities 2 to 88.2. And in the adaptively chosen ciphertext setting, the data complexity is 2 to 84, and the time complexity is 2 to 83. Now we briefly recall the Boomerang distinguisher. Boomerang attack is an extension of differential cryptanalysis in the adaptive setting. Its goal is to estimate the boomerang probability, P sub B. Suppose the cipher E is decomposed as 2 parts, E sub 0 and E sub 1. For E sub 0, there exist differentials alpha to beta with probability P right arrow. For E sub 0 to -1, there exist differentials beta to alpha star with probability P left arrow. For E sub 1 to -1, there exist differentials delta to gamma with probability Q. Then the boomerang probability P sub B is estimated by P right arrow, P left arrow, Q22. The boomerang attack is then extended to the sandwich attack, where E is decomposed as 3 parts, and the connection probability for the middle part is R. Then the boomerang probability is estimated by P right arrow, P left arrow, Q22 times R. Our motivation is as follows. Firstly, the distinguishers on 5-round AES have the very low data complexity, but the best distinguishers on 6-round AES have the data complexity 2 to 84. It's very high. How to shorten this gap? Secondly, the attacker is provided a wider space in the adaptively chosen plaintext and ciphertext setting. How to fully utilize the advantage
Sorry,
of
Yan.
Yeah.
So please get rid of your smaller window because it's blocking the view.
my smaller
You
window?
have a smaller window blocking the top right corner of the presentation screen. Yes, now it's fine. You can carry on. Now it's fine. You can go ahead.
Sorry, let me adjust my window.
Yeah, now everything is okay. You can go ahead.
Now can you see my screen?
Yes, we can see your screen.
Okay. how to fully utilize the advantage of this setting to develop new cryptanalysis technique. Thirdly, Boomerang cryptanalysis has shown the power for many block ciphers. The classical Boomerang distinguishers usually uses only one Boomerang property, whether we can use two or more Boomerangs to enhance the distinguishing effect. In fact, our paper combines two and more related Boomerangs to form the reboomerang and boomerang chain distinguishers. We first introduced the framework of reboomerang distinguisher by combining two boomerangs. Assume the cipher E is decomposed as three parts, and assume that there exist two boomerangs, B sub 1 and B sub 2, with probabilities of P sub B sub 1 and P sub B sub 2 respectively. The correlation between B sub 1 and B sub 2 is that they have the same truncated differential trail over E sub 0 in the forward direction, D sub in to D sub out, of which the probability is P right arrow. A plain text pair is called a red pair if it follows the truncated differential trail over E sub 0 in the forward direction. For a plain text pair P sub 1, P sub 2, another plain text pair P sub 1 prime, P sub 2 prime is called a friend pair of P sub 1, P sub 2 if they have the same difference and the active cells of P sub 1 prime, P sub 2 prime are the same as them of P sub 1, P sub 2. It's ensured that any friend pair of a red pair is also a red pair. Distinguishing the cipher E by B sub 2 needs about P sub B sub 2 to minus 1 chosen plaintext pairs, where P sub B sub 2 equals P right arrow, P left arrow, Q2 to R. If all plaintext pairs chosen are red pairs, it can be reduced by a factor of P right arrow to minus 1. Now the problem is how to get a red pair. A plaintext pair chosen randomly is a red pair with a probability P right arrow. If by a related boomerang B sub 1, we can get a target set of size L less than P right arrow to minus 1, which contains one red pair, then the complexity will be improved from P sub B sub 2 to minus 1 to L times P right arrow times P sub B sub 2 to minus 1. The first step of the reboomerang distinguisher is that we use the boomerang B sub 1 to obtain a target set of size L less than P right arrow to minus 1, containing one red pair on average. We choose P sub B sub 2 to minus 1 plaintext pairs, such that the differences belong to D sub in and perform B sub 1. If there exists a returned pair satisfying the boomerang property of B sub 1, then save the plaintext pair in the target set. In this way, there is one red pair in the target set on average. Besides one red pair, the target set also contains some random pairs satisfying the boomerang property of B sub 1. Their expected number is P sub B sub 1 to minus 1 times P sub R sub 1, where P sub R sub 1 is the probability of a random pair satisfying the property of B sub 1. After obtaining the target set, the second step is that for each plaintext pair in the target set. We construct its p right arrow times p sub b sub 2 to minus 1 front pairs and input to the Boomerang b sub 2 to distinguish the cipher. For the cipher E, the input pairs contain p right arrow p sub b sub 2 to minus 1 right pairs, and there exists one pair satisfying the Boomerang property of b sub 2 on average. For random permutation, the number of pairs satisfying the property of b sub 2 is L p right arrow p sub b sub 2 to minus 1 times p sub r sub 2, which is less than 1. Then the cipher can be distinguished. Now we present the exchanged boomerangs for 6-round AES by combining truncated boomerangs with exchange technique. Decompose 6-round AES as 3 parts, where E sub 0 is the upper 2.5 rounds before missed columns of the third round. E sub m is the middle 1.5 rounds, and E sub 1 is the final 2 rounds. For the upper part, E sub 0, we consider truncated boomerang trios. In the forward direction, the trio is D sub in to D sub out, of which the probability is p right arrow. In the backward direction, the trio is D sub out to D sub in star, of which the probability is p left arrow. For the lower part, E sub 1, we exchange the inverse diagonal of ciphertext pairs so that the probability Q equals 1. We first choose ciphertext pairs C sub 1, C sub 2, which have T in active inverse diagonals, and then exchange one active inverse diagonal to obtain 4 minus T new ciphertext pairs C sub 1, C sub 3 to G, C sub 4 to G. Since E sub 1 can be seen as 4 super S boxes applied in parallel, so we have that Y sub 1, Y sub 2 have T in active diagonals, and Y sub 3 to G, Y sub 4 to G can be regarded as exchanging one active diagonal of Y sub 1, Y sub 2. For the middle part E sub m, 0, 1 gives a lower bound of the connection probability R by analyzing a special case. Then we can estimate the probability of the exchanged boomerang for 6-round AES. The first exchanged boomerang trio B sub 1 of 6-round AES, which is used in the reboomerang distinguisher, is shown on the screen. The boomerang probability P sub B sub 1 is 2 to minus 101.84. When using the plaintext structure, 2 to 38.84 plaintext structures are needed to form 2 to 101.84 input plaintext pairs. The probability P sub R sub 1 of a random pair satisfying the requirement of B sub 1 is 2 to minus 89.84. After applying B sub 1, the number of pairs in the target set is 1 plus 2 to 12. The detail of the second boomerang B sub 2 is shown on screen. The boomerang probability P sub B sub 2 is 2 to minus 88. For red pair, the probability of B sub 2 is increased to 2 to minus 66. Then for each plaintext pair in the target set, we construct 2 to 66 front pairs to input B sub 2 to distinguish 6-round AES. The target set contains 1 plus 2 to 12 plaintext pairs. Then the total number of input pairs of B sub 2 is about 2 to 78. When using B sub 2 directly as a distinguisher, The input required is 2 to 88 plaintext pairs. The reboomerang technique reduces the number of input pairs by a factor of 2 to 10. The complete process of reboomerang distinguisher for 6-round AES is shown on the screen. The data and the time complexities of a distinguishing process are both 2 to 81.33, and the success probability is about 40%. To improve the success probability, we can repeat this process twice. Then the success probability can be improved to 64%. The total data and the time complexities are both 2 to 82.33, and the type 2 error probability is about 2 to -13. To improve the complexity, we insert a new boomerang B sub m in the middle of the reboomerang distinguisher, which can be used to reduce the size of the target site. The truths of B sub m are the same as those of B sub 1 over E sub 0, and the other truths are the same as those of B sub 2. For red pair, the probability of B sub m is 2 to -57.42. For each pair P sub 1, P sub 2 in the target site, we construct its 2 to 57.42 front pairs and input them to B sub m. If the boomerang property of B sub m is not satisfied, then we delete the corresponding plaintext pair from the target site. If P sub 1, P sub 2 is a red pair, it will be kept in the target site. The boomerang property of B sub m is satisfied randomly with probability B sub r sub m equals 2 to -59.42. Then if P sub 1, P sub 2 is not a red pair, it's kept in the target site with probability 2 to -2.18. After B sub m, the size of the target site is 1 + 2 to 9.82. To further improve the filtering probability of B sub m, we increase the number of front pairs to 2 to 57.42 times n. If the number of pairs satisfying the property of B sub m is less than n, we delete the corresponding plaintext pair from the target site. Then the probability that a wrong pair is kept in the target site is related to the parameter n and is denoted by P sub f of n. After filtering, the size of the target site is 1 + 2 to 12 times P sub f of n. The corresponding complexity and the success probability can be estimated. The best triple boomerang distinguisher for 6-round AES has data and time complexities of 2 to 77.82, and the success probability 66%. By further extending the triple boomerang distinguisher, we can obtain the general boomerang chain distinguisher by 2 improvements. Firstly, we repeat the middle boomerang trio B sub m several times in the middle to further reduce the size of the target site. Secondly, we increase the input data size for each boomerang to improve the success probability of the distinguisher. The complexity and the success probability of the boomerang chain distinguisher can be estimated. Finally, we obtain the best boomerang chain distinguisher for 6-round AES with data and time complexities 2 to 76.57 and the success probability 60%. To verify our boomerang chain technique, we mounted an experiment to the small-scale variant of AES with 64-bit block. We implement 500 experiments for random case and plain text structures. The experimental success probability on small-scale AES is about 69%. In conclusion, we extend the classical boomerang distinguisher to combine two or more related boomerangs with the technique of front pairs and propose the reboomerang and the boomerang chain distinguishers for 6-round AES. The boomerang chain distinguisher for 6-round AES has the data and time complexities 2 to 76.57 and success probability 60%. Compared with the previous best result, the data complexity is reduced by a factor of 172, which is a new record for 6-round distinguisher on AES. I'd like to end my report. Thanks so much for your attention.
Let's thank the speaker. Any question from the audience? Okay, so I have one quick question. So have you studied how with the number of rounds increasing, how the complexity or the success probability changes? So that might give an idea whether it can be extended to higher rounds or not.
Yes, actually, we have considered the distinguisher for 7 rounds of AES, but not at current there exist no boomerang distinguishers for 7-round AES, and when we try to construct it, the probability is too low. So there's no result now.
Okay. Yeah, not an issue. So if there are no more questions from the audience, let's thank the speaker and also all the speakers of this session.
Okay, thank you.
So we have coffee break now, and we'll assemble again after the break.